Welcome everyone to week 8 of this PMRF TA sessions for the NPTEL course Approximate Methods in Quantum Chemistry. A brief intro of mine. I'm a PhD student PMRF in the Solid State and Structure Chemistry Unit SSU at the Indian Institute of Science IEC Bangalore, and I'm an NPTEL PMRF TA for this course Approximate Methods in Quantum Chemistry, and we were having a total 8 2-hour interactive problem solving sessions since February 4, every Saturday from 6 p.m. to 8 p.m. and today is the last session on 25th March of week 8. Okay, right, alright. So in this session we are going to solve the problems related to week 8 content, and in week 8 you guys studied about time dependent perturbation theory. Let me just check. Alright, so you guys learned about time dependent perturbation theory and its applications, and we are going to solve problems related to that. Alright, so let's go to our first problem. So in first problem what we have is the problem 1 is suggest how you could prepare a degenerate two-level system in a mixed state in which there is equal likelihood in finding it in either state. Okay, so this is our problem. So we have to suggest like how we can prepare a degenerate two-level system in a mixed state in which there is equal likelihood of finding it in either of the state. So while looking at this problem, okay, so we need to basically find such that we have a system which is mixed by two degenerate state, and the probability of and we have to mix it. The mixture should be like mix means the composition of or the which is given by the coefficients for each of these states. So the coefficient should be such that when we find the probability of finding the system to be in either state 1 or state 2, then we should get half. So that is what the question is asking us for. Now we know to prepare this. Now we know that state now we know that if we don't provide any perturbation to our system, so what you studied from this time dependent perturbation theory, so we know that if we don't provide any perturbation to our system, then the 1 minute. Sorry about that. There was some technical problem, I guess. Okay. Okay, alright. Let's go back to the problem. It is being recorded. Yeah, this is recording 3. Sorry about that. Alright. Alright, so okay. Now we know that if we when we don't provide the perturbation, so basically it is given for 2 states. So what you solved in the class as well. So if we have, so we solved for coefficient. We solved that if we take just 2 states and then we took we took time dependence of these coefficients. So what we obtained, if you remember, you obtained these two. You will obtain these two equations: 1 upon iota h cross C2 for some perturbation H12 prime T. This is our matrix for our perturbation. E to the power minus iota omega 21 T, and then we have C2 dot equals to 1 upon iota h cross C1 H21 prime of T e to the power iota omega 2. Okay, so you can check the lecture notes, and you can see that these equations were derived for if we just consider the two states in the time dependent perturbation series, like you have provided some time dependent perturbation, and thus your coefficients will also have some time dependence of each of the state. Now in the absence of perturbation, we now during now for this case we know that in the absence of perturbation, so if there is no perturbation, then we know that basically our H, what this means that our H, this matrix elements H12 prime of T will be equals to H21 prime of T. I can write as 0 because there is no perturbation, so this matrix elements will be 0. So that will give us C1 dot will be 0, C1 dot will be equals to C2 dot, which is change of C1 C2 with respect to time, this time, okay. So that will be equals to 0. In that case, our wave function is x comma t, that will be okay. So x comma t will be equals to, so what happens since this C1 dot C2 dot 0, what we get is C1 of 0 psi1 naught, which is our state 1 without perturbation, e to the power minus iota our frequency of that state t plus C2 at t equals to 0, whatever the coefficient water at t equals to 0, psi2 of 0 of x e to the power minus iota omega 2 t. Alright, so what this shows is that, okay, so what will happen if there is no perturbation? We know that if there is no perturbation, then my wave function will oscillate with time, but the compositions doesn't change. So if there is no perturbation, then the composition will not change. Okay, so in the absence of perturbation, the composition of both the wave function will be fixed. Now in this case, the question is asking us, like, we have to prepare this mixture of the system, and we have to make it like we have to prepare such that it will have equal likelihood. So it means that basically what we suggest is that we have to somehow provide a perturbation such that the probability will change. So initially, let's take we will take the same example as taken in the lecture. So we will consider our initial state is like we will consider our initial condition. So let's say we have two degenerate states. Okay, initial condition, we will have that C1 of 0 equals to 1. So we are initially in state 1, and C2 of 0 is equals to 0. So basically we are initially in state 1, and C2 of okay, and thus C1 is 0 and C2 is 0. So probability of finding the system in state 1 will be 1. So P1 at 0 will be equals to 1, and P2 of 0 P1 of 0 will be equals to mod of C1 at t equals to 0, which will be equals to 1. So P1 of 0 will be equals to mod of C1 of 0 square, which will be equals to 1, and P2 of at t equals to 0 will be equals to C2 at t equals 0, and since that is 1, that has to be 0. So initially we are considering our system is in state 1 only, and state 1 and state 2 are degenerate. State 1 and state 2 are degenerate. Alright, so these are degenerate state. So that means omega 2 1 will be equals to 0. Okay, so our omega 2 minus omega 2 1 we know is basically omega 2 minus omega 1. Alright, so omega 2 1 will be 0 because these are degenerate states. because these two are degenerate. Alright, so now what we have to do so that a probability with this, so that we have run right. Okay, so we know that we derived the Rabi's formula, if you remember. So in the lecture notes we derived the Rabi's formula for this two-level system when we apply a constant perturbation. So to solve this problem, to get the equal probability now, what we suggest that we have to use this Rabi's formula, and then we have to find, okay, when we applied this some perturbation, like say we apply some constant perturbation, for how long we have to apply that constant perturbation. So we have to apply the constant perturbation till this the probability of that state 2 of going to state 2 will become 0.5, and then we will suddenly stop that perturbation. So as soon as we will stop that perturbation, what will happen? The composition will be fixed. So our composition, we will apply the perturbation till the composition becomes 0.5, and then we extinguish the perturbation. So the perturbation will be gone, and as soon as the perturbation is gone, there is no perturbation. Then we know that as we have seen here, the composition will be fixed. And thus we will have created a system where there will be the probability of finding a system at any time. After that, at any time, the probability of finding a system in any of the state will be 0.5. So the likelihood, what was asked in the question, the likelihood of finding it in either state will be equal. Alright, so this is what we have to do. So for that, first we will write the Rabi's formula. Rabi's formula. Sorry, it is Rabi's formula. Rabi's formula, and that is given by P2 of t is equals to, if we calculate the mod of C2 square, now that is given by 4 times mod of B square divided by omega 2. So I'm writing the general formula first, which we obtain if we apply a constant perturbation. 4 mod of B square times sine square of omega 2 square is 4 times omega 2 square times t. Alright, so this is our Rabi's formula. Here omega 21 equals to 0, we have degenerate states. Alright, so what we get, our P2T will just be given by and now since we are writing this, our perturbation, so the perturbation that I will apply, or let's do this like this. Okay, so that will be equals to, you can see that will just come as sine square. Okay, so for omega 21 equals to 0, then this 4 mod b square both will cancel out, and we get 2, and we get sine square mod of b square root mod of b times t. Okay, this. Alright, and here our perturbation also, h prime of t is basically what we have taken is a constant perturbation h cross b. That's why we are writing this Rabi's formula. Okay, so this is our perturbation. This is the perturbation that we have applied to our system, and we know P2T from our Rabi's formula. Now here, from this equation, you know that, okay, from here basically we know that if you remember, basically what this gives us is that if we have a time, so we have 0 here, we have 1 here, and what we want is 1 at 0.5. So this is our P2T. So our P2T initially is 0. At t equals to 0, we have taken P2T is 0. So since this will be a sine function, this will go like this. Okay, so this will become 1 even if the perturbation is very small. Alright, and this will go like this. Alright, so it will go from 0 to 1 and so on. Alright, so this will be our P2T. P2T. Alright, and similarly we will have P1T, which is 1 initially and will go to 0, and it will also slide like this, because P2T, P1T is just 1 minus P2T. This will be our P1T. And what we want is, we want this to be at half. Alright, we need to find a time when both of them are at half, and I guess you can see that half will be this, but you can see that okay, this will be sometime half. So at some time, after some time, let's say this time T naught, okay, we can see that both the probabilities will be same, and we need to find that this time T naught. And what we will do is, we will remove this perturbation after this time T, and so both the probability will decrease. So the probability of P1T will decrease from 1 to this 0.5 and from 0 to 0.5, and then when we will remove it, both of them will just go. So you can think that okay, so as soon as we will remove the perturbation, both of them will be constant throughout if we will remove the perturbation. Okay. Remove perturbation. Okay, so at T equals to T naught, we have to remove the position. And what is T naught? T naught is basically P2 at T naught, we know is equals to 0.5. So basically what we have to find is that sine square mod of V at T naught, that has to be equals to half. We just write it as half. So that is sine function, sine is 1 by root 2. So our T, you can check, will be equals to pi upon 4 mod of V. You can put like pi upon 4 mod of V will cancel out. It will be pi by 4, sine pi by 4 is 1 by root 2, square is 1 2. Okay, so that is our T. Alright, so we can basically from here we can write our answer. Okay, so we have find T naught equals to pi upon 4 mod of V. So from here we can write it as, therefore right, so using this, therefore the perturbation should be applied to a system that is known to be in state 1 initially. So that is what we have taken and removed. Then the perturbation is known to a system that is known to be in state 1 initially, and then the perturbation is removed. So it doesn't matter, as we know, the magnitude of this perturbation doesn't matter. It will go although that so yeah, the magnitude will define our tutor. So if the magnitude of the perturbation is small, then the time it will take to reach that 0.5 will be larger, so our T naught will be larger. And for higher perturbation magnitude, if mod of V is large, then T naught will be small. And the perturbation should be applied and then remove, and then let us say, and then remove at T equals to T naught equals to pi at 4 mod of V where there is T equals to T naught equals to pi upon 4 mod of V. Now, although the wave function of the system will oscillate the probability of finding the system in either state will remain 0.5 until another perturbation is found. So what we discussed in the start, what I discussed in the start. So if there is no perturbation, then the composition will remain fixed. So I'm just writing it down in this form. So what will happen is that you can, so basically we applied it up to this, and for T prime greater than T naught, for T prime greater than T naught, there is no perturbation. Basically there is no perturbation, mod of V equals to 0, we can see. So in that case, what will happen is C1 of T prime will be equals to C1 at T naught, and similarly C2 at T prime will be equals to C2 at T naught. So the probabilities will be fixed, will be frozen. The P1 of T prime will be equals to 0. Will be equals to P1 at T naught, which will be equals to 0.5. Similarly, P2 at T prime is equals to P2 at T naught, which will be also equals to 0.5. Right. So we have created a. So this is how we will create this kind of system. Now this is an aside. There's an interesting fact. This state equation procedure is the quantum mechanical basis of first technique and nuclear magnetic resonance. If you might have heard of NPTEL-PMRF state preparation technique that we discussed in this problem. This is actually the quantum mechanical basis for this for the pulse technique in this nuclear magnetic resonance, which is NMRs, nuclear magnetic resonance. Okay. All right. Let's move on to problem number 2. And problem number 2 is actually the similar problem that we just solved. But now in this thing in this problem what we have to do is like we have to suggest how you could prepare a degenerate two-level system in a mixed state in which the probability is 1/3 of finding it in state 2. So now we have instead of 0.5 it is 1/3. So that doesn't matter. But the procedure will be same. So basically from this one we can see that we can basically make different kind of composition. So even if we start with our same initial condition, we will start with the system is in some state 1 and 1 only, and using this method we can prepare any kind of mixture. So we will just provide some the basic idea is same. We will just provide some perturbation up to a fixed level of time, and from the Rabi's formula we know what is the probability P2T is, and whatever the P2T composition we want at the end, we will just equate it to our Rabi's formula, and then we will find the time up to which we have to apply the perturbation. So the procedure is the same. So again we will have the initial at t equals to 0. We know that C1 of 0 we are considering 1, and C2 of 0 0. So our system is in state 1 at t equals to 0, and for again we have a degenerate for degenerate two-level system. Alright, so we have P2 of t. Again we have just solved that will be this. So now we have to basically use this formula to find the time for which our P2T, so that at t equals to t naught. So t equals to t naught. What we have is we are saying that Pt of t naught is equals to 1/3. So we just need to find this t naught. So just put the formula here, and we have 1/3. This will become sine inverse of 1/√3. So our t naught will be equals to sine inverse, or you can say 1/√3 divided by mod of e. You can find whatever that t naught exact value is, but the basic idea is just the same as this solved. So basically the idea is that the perturbation should be applied for from t equals to 0 to t equals to t naught, and then we will. Alright, so this is the basic idea how to prepare this kind of mixed states. Alright, let's moving on to next problem. Okay, problem number 3. So okay, let's see the problem C. So in problem number 3 it is given that calculate the transition rate from the ground state of a molecule to a continuum of states if the transition matrix element has a constant value of 4.5 into 10^12 radian per second, and the continuum consists of 2.5 to 10^4 states in an energy range of 1.5 attojoule accessed by the transition. Alright, so this Aj is attojoule, so let me just write it here like 1 attojoule is equals to 10 to the power minus 18 joule. Right? This one attojoule. Okay, so 1 attojoule is equal to 10 to the power minus 18 joule. Alright, so this is the problem now. So for this problem, we know that the transition rate to a continuum of states is given by the Fermi-Gordon rule. Right, so we are going to use the Fermi-Gordon rule. So it is we derived it using the continuum states, like the initial states there and the final states. They are in a continuum. So it is a similar problem. So we will use the Fermi-Gordon rule. Right. So the Fermi-Gordon rule is given by, we are going from initial to some final states. That is given by 2 pi h cross V of Fi square, the rho of energy of E of Fi, where this transition matrix element that we are talking, that is talked in the problem, and it is given that transition matrix element value, it is a constant value which is provided to us 4.5 to the power 12, and this rho is basically the density of states. And the transition frequency. Okay, so we need to calculate this transition rate, and this transition is given by our Fermi-Gordon rule, and transition matrix element is given to us, and we need to find this density of states. For this, some information has been given to us. We have given that the continuum states, the total number of states are given, and the energy range is given. So density of states is just the total number of states in per unit energy range. So we can basically find this density as well. So we know that the molecular density of states. So this density of states at the transition frequency basically will be considered. We will take this as this molecular states for which the information is given. So the molecular density of state, this rho m, will be given by, okay, the total number of states are given to us is 2.5 10 to the power 4 within a range of 1.5 attojoule, and 1 attojoule is 10 to the power minus 18 joule. So we have 1.5 into 10 to the power minus 18, and if you calculate this, you will get 1.67 into 10 to the power 22 joule inverse. It will be joule, correct? This attojoule. Alright, so we will get 1.6 into 10 to the power 22 joule inverse. So now we have this, instead of rho, we have rho m. V of Fi is already provided to us. So we will just have to put this in our formula. So our transition rate going from that initial to final state, which is given by this formula 2 pi h cross mod of V square rho m. So we will have 2 pi h cross the value. So for h cross, the value will be 1.055 into 10 to the power minus 34 joule second. Right. For mod of V square, so mod of V, the matrix element is given as 4.5 to 10 to the power 12 second inverse. So 4.5 into 10 to the power 12 second inverse whole square and then we will have our rho n, which we just calculated, which is 1.67 into 10 to the power 22 joule inverse. Alright, so we can calculate, and what we will get this transition rate W from this initial to this final state. That will come as 2.24 into 10 to the power 14 second inverse. Alright, the units are correct. The 2.24 10 to the power 14 second inverse will be our answer. Alright, so we have so this is how, by using Conformy's golden rule, we can find this transition rate going for any molecule. Transition rate of a molecule to a continuous state, going from its ground state to a continuous state. Okay. So that is done. Let's go to next problem. Alright. So alright, so that is this. Okay. So let's go to the next problem. Just alright, let's solve our problem number 4. Okay, so problem number 4 is estimate the lifetime of a molecular state if the uncertainty in its energy, that is the range of energies present in the state, is 1.9 to 10 to the power minus 24 joule. So as you know, as discussed in the class at the end, when we discuss the Einstein's coefficients. So we know that if the lifetime, basically if the system has a particular lifetime, like if the system is not staying, like it doesn't have an infinite lifetime, like the system will remain in this state forever until some like perturbation, but perturbation applied or something. So then the system doesn't have a fixed energy, so there is some uncertainty in its energy, and that has its relation with its lifetime, with the lifetime of that molecular state as well. So this relation is given by let's use the black color. Okay. Alright, so this relation of this lifetime with this uncertainty of the energy of that state, that is given by the lifetime broadening relation. Alright, which is given by tau del E equals to H cross. So this is the relation where you can see this lifetime broadening relation, where this tau will give you the lifetime of state that we have to find, and del E is the uncertainty in energy. So it will be the uncertainty in the state's energy. So this just this simple formula, but there are some points. So this is just a formula based problem, but still there is this thing that we should understand, that the lifetime broadening relation is okay. Let me just write it in blue because that is an important fact actually. That's not lifetime it shows that the shorter the lifetime of the state, the rest size is its energy. Okay, so we can see it here. Okay, so like Delhi will be h cross by tau. So if our lifetime is very small, so then h cross by tau will be a higher value. So delta, so the uncertainty in its energy. So the uncertainty will be larger if the lifetime is smaller. So basically from here we can take 2 points when a state has zero lifetime, zero lifetime. So basically what I'm saying is that this tau is 0. Tau is 0. We can say nothing about its energy. Alright, because when tau is 0, what will happen? Del of E is infinite. So basically there is a complete uncertainty about the energy of that state. Okay, so delta E will be infinite if tau is 0, the lifetime of that state is 0, then there is uncertainty, complete uncertainty about what is the energy of that state is. So we can't say anything about its energy, and only when the and actually this is right, only when the lifetime of a state is infinite. Okay, so tau is infinite, which is like tau equals to infinity. Can the energy be specified exactly? Alright, so basically infinite lifetime is infinite. Basically the system will not go to any other state. The system will remain the state until like you apply give it some energy or something. So in that case, like T is infinite, then delta is basically 0. So then we know, then we can specify the energy of the state exactly only. Then only we can specify its state exactly. Otherwise we cannot. Alright, so this is about the lifetime broadening relation. Now back to our problem. So if you just go back to our problem, so for solving the problem is we just need to find a lifetime, and this is just a formula base from using this lifetime broadening relation. Tau, this is our lifetime, equals to h cross upon del E, uncertainty in the energy which is already provided to us, and again h cross 1.055 into 10 to the power minus 34 joule second, and this is given by the uncertainty already given to us, 1.92 10 to the power minus 24 in joule only, 1.92 into 10 to the power minus 24 joule. So if you calculate, tau will come as 5.49 into 10 to the power minus 11 second. So using this formula, we can find the lifetime of the molecule states. Okay, now our next problem. So in next problem number 5, what we have to do is we have to calculate the rates of stimulated. So okay, so we have to calculate the rates of stimulated and spontaneous emission for the 3p to 2s transition in hydrogen when it is inside a cavity at 1000 Kelvin. Alright, so so from the problem, like we have to calculate the stimulated and spontaneous emission. So basically we will have to go to the Einstein's coefficients. Coefficients. Okay, so let's go to problem number 5. So in problem number 5, we have to calculate the rates of stimulated and spontaneous emission for the 3p to 2s transition in hydrogen when it is in a cavity at 1000 Kelvin. So seeing this stimulated and spontaneous emission, so we know that we have to go to Einstein's coefficient. Now for Einstein's coefficient, we know that for absorption, we know that a transition going from initial to final, we are going from actually rounds it off. So this is not, absorption is not asked in the question, but just for the sake of completeness I am writing absorption here. Okay. Then for stimulated emission, okay, so we have to find the rates only. So that this is the rate for the absorption. For stimulated emission, is rate going from this final to initial is given by VFI, the radiation speed of Fi energy. Okay, so this is equation 1, this is 2. Absorption rate, stimulated emission rate, and the spontaneous emission rate. We are given in terms of this Einstein coefficient. We can find initial, spontaneous, this is F5. Alright, and then we also know that, okay, and then what we do, okay, initially if there are Ni is the number of states in the initial state, the number of states, or the number of particles, you can say, in state I are given by Ni, then they are decreased by BIF. times rho radiation, which is the absorption, E of Fi, absorption rate. Now that absorption rate will be equals to both the emission rate, which is NF times the number of particles at any time t in NF is equals to A Fi spontaneous emission plus BFi radiation of A of Fi. Alright, and then we know that NF upon Ni gives e to the power minus E Fi by kBt, which is the Boltzmann distribution. Right. And using this we can find rho radiation E of Fi is equals to A Fi divided by B Fi. Okay, and here this BFI will be equals to BIF. Here BFI will be equals to BIF. Alright, divided by because they are emission, we can say they are equal, or we will see that okay, as you have seen in the class from this, here also we will derive the same thing. AFI divided by BFI, BIF divided by BFI, e to the power EFI by kBt minus 1. Alright, so this is the relation that we get in terms of the Einstein coefficients, and then we know the Planck's distribution. Which gives us the density of states for EM field. That gives us radiation E of Fi equals to 8 pi h. So this is the Planck's distribution that we already have, and then we can just compare these two. Okay, and by comparison we obtain that EIF is equals to BFI. Alright, because you can see that there is 1 here, so EIF has to be equals to BFI, and we obtain this relation, which is AFI is equals to 8 pi h divided by c cube. This is the 8 pi h by basically mu of Fi whole cube B of Fi. So and so we have to so this we already know, and these are the relations between this we know, and so we are going to use the formulas that I have written. These formulas we are going to use what we have seen in the lectures for this problem. Now for this problem I would also provide a reference. There is one more thing for this particular problem actually, since what we will need is to calculate the transition dipole. And to understand like from where this formula is, I would suggest I will provide this reference. So you can go to this reference, which is the Okay, first the book name. Book is molecular quantum mechanics. So this is the reference book, and in this reference book, chapter 6, the techniques of chapter 6, techniques of approximation. Please go through the further information. You can either basically I will provide the formula, but you can refer this book's further information to understand where this the type of formula will come. Electric further information, it is electric dipole transitions. So please refer to that sections for the formula that I am going to use for this problem, other than the formulas that we already know and we just discussed. So for now, for this problem, basically, so what we have, we need to find this rate of stimulated emission between this kind of transition where we have a transition from like 3p orbiter to 2s orbiter. So these kind of transitions are like are electric dipole around kind of transitions, and for this kind of transitions, so this will be equivalent to like some electric dipole around transitions, and that's why I'm referring to this section in the chapter of this book. So please find it, so that will help you to better understand where this formula is coming. But basically, we are just going to use this simple as, so like for electric dipole around transition, transitions, if you go to this reference, then you find that this coefficient Einstein's coefficient P, which is for the absorption rate, or here it is the stimulated emission rate, that coefficient, that is given by mu vector Fi mode square divided by 6 epsilon naught h cos square. Alright, where epsilon naught is the permittivity of vacuum, constant that you know, and h cross the Planck constant, reduced Planck constant. It is the permittivity rate, and there this mu Fi vector that you might have seen now is the transition dipole. So basically, this is the thing. So basically, we need to find this transition dipole moment, and our this Einstein coefficient, which is related to the stimulated emission, that is given by this mod of mu square divided by 6 epsilon naught h phi square, and this is given by this mu Fi vector, that is by whatever our wave function, final wave function is, mu cap psi I t tau, where this is the electric dipole moment. Right. So basically, this is the formula that we are going to use, and for this you can go to that reference and understand how this formula comes. But basically, this is the reason, and basically we just need to find this transition dipole moment. We need to find this thing, transition dipole moment, which is given by this, and then we just have to put that transition equilibrium in the above formula, and that will give us our this coefficient for stimulated emission. And then if we know the stimulated emission, then we can find this another coefficient as well from this relation between Einstein's coefficient. We can find for the spontaneous emission, we can also find our Einstein coefficient. And then to find the rate, then we will go to these formulas. The spontaneous emission rate will just be this Einstein coefficient, and we will also need to find this new frequency as well first for that. So we have to find the from the energy difference basically between the final and the initial state, we can find this new frequency. So, and from there we can find this spontaneous emission rate, and for the stimulated emission rate we also need to find this low radiation EFI. And for that what we are going to use, we are actually going to use this you can use this we will use this Planck constant formula, because then we can use any of the formula. You can use this formula or this formula, but it will be like if you just need to put nu and E of Fi, so that will just provide you from the Planck constant itself we can get this low radiation density of states for this problem. Okay. So going back to our problem. So now, so we know what are the things that we have found. So first we have to find the transition dipole moment nu z for the EPZ to 2s transition. Right. So basically, first we will find this nu z, because so basically the transition that we have seen that is asked is from 3p to 2s transition in hydrogen. So for that one transition, we will have transition from 3pz 3px 3p by 3pz. So first we will find for 3pz because that is easier. So nu z will just be given by psi 3pz star. Now this nu k will be given by minus E times z, the dipole moment operator. The vector dipole moment operator for this case will be given by minus E times z, and psi 2s times d tau. Now for this we need psi 3pz and psi 2s, and these are for the hydrogen atoms. So now for hydrogen atoms, now for this also we can find this thing. So for hydrogen atom, hydrogen orbitals, okay. So the hydrogen orbitals will have the Rnn and Yln. So we know that is Y psi nln will be equals to Rnn and Yln. We have a linear function in spherical harmonics. So linear functions Rnn and spherical harmonics, orbitals, linear functions, and spherical harmonics. Harmonics which are Yln. Refer table 3.4 and table 3.2 of the reference chapter 3. So from the scene books chapter 3 you can find in table 3.4, 3.2 you can find these area function. You can do this integration. Alright. Basically, if we do this integration, then nu z comes as minus 1.769 e into denominator whole radius, or basically you can find as minus 1.5 into 10 to the power minus 29 coulomb meter. Alright, so we can find this nu z. Now other than mu z, you can understand, like for 3pz we have mu z. Now similarly we will have this dipole we will have the transition dipole moment for px and 3px and 3py orbitals as well. Now since this 2s orbital is symmetrical, then we know that the contribution from all three of them will be same. That's we are writing. Now since the 2s state of the atom is very symmetrical, the contribution So since our 2s orbital is spherical symmetrical, so the contribution from both 3px, 3py and 3pz are identical. Therefore, basically we don't need to calculate this transition transition dipole moment for this x and y direction, because we know that since they will have the same contribution, so the the mod square will basically be same. So basically mod square mu x square plus mu y square plus mu z square, that will be equals to 3 times, you can just say mu z square, because all three of them will have the same contribution, and we have already calculated this value, so we just have to take the square of this and multiply it by 3, so that will be approximately equal to 6.75 into 10 to the power minus 58 coulomb square. Alright, so we have found this new square. So now the Einstein coefficient of stimulated emission that will be given by, I'm denoting this by just B, so we know that they are just B and A only, so I'm denoting now this by B, and this will be mod of mu square divided by 6 epsilon naught h cross, and that if you calculate by putting other values, that will come as 1.143 into 10 to the power 21 joule inverse into Q. Now we have found B. Now to find A, we have to use this formula 8 pi h upon c cube. So we have the B value, but we also need to find this frequency, nu Fi. So this frequency, the frequency of the transition is 567 into 10 to the power 14 hertz, where this is just our variable constant. So that is just from the hydrogen atom energy formula, so that you can check. Now since we have the frequency, we have our B coefficient as well, so now we can find our coefficient A. So the Einstein coefficient spontaneous emission that will be given by A is equals to 8 pi h nu cube divided by c cube times B. That will be equals to 6.728 into 10 to the power 7 seconds. Okay, so we just need to put this value. We have the new, we have B as well, and all the constant values, and you can, and the result will be 6.728%. So we have the A value. So and the last thing, now we need to find this rate, stimulated emission rate and spontaneous emission rate, and for that we need to find this rho, and we are going to use you can use this Planck's formula or this formula, but let's just use this Planck's formula, because then we just have to, the variables are just this nu and nu we already found, and that will be energy E. So energy E and nu will be our two variables, and otherwise we will have kind of three variables. We will have energy E, A and P as well. So at 1000 Kelvin, and for the transition frequency nu, we can find low radiation using the, let's say, the Planck's formula, Planck's distribution, 8 by h nu by c cube e to the power h nu by kBT. So this is the energy. So basically we don't have two variables. Basically we just have if we use the Planck's formula, then we just have the one variable nu only. Otherwise we will have to put the value of coefficient as well, and in Planck's formula we just make the nu, and all the others are just the universal constants. So 8 by h nu cube by c cube into by h nu by kBT minus 1. So just put the value of nu in here, and the value of temperature T as well. So we have this one variable T, but T is also fixed, like it is 1000 Kelvin. It will be same for both the formulas. And the answer that you will get is 1.782 into 10 to the power minus 23 joule hertz inverse per meter cube. Alright. So plus 72 10 to the minus 23 joule hertz inverse per meter cube. So now we can find our final, so our rate of stimulated emission from our initial formula. We get B times this low radiation that we have calculated. Now our P is 1.143 into 10 to the power 21. 1.143 into the number of joule inverse meter cube. Joule inverse meter cube. And we have rho radiation, which is given by 1.7882 into 10 to the power minus 23 joule hertz inverse per meter cube. Right. So Okay, so from here you can see joule inverse joule cancel out, meter cancel, and ours is second inverse, second. We can answer in second inverse only. So the units are right. And what we will get is this rate of stimulated emission defined as 2.036 into 10 to the power minus 2 second inverse. Alright. So let's check it. And for rate of spontaneous emission, that is just given by our coefficient A, which is equals to 6.728 into 10 to the power 7. Alright, so these are our answers. Let us rate of stimulated emission is given by this, and rate of spontaneous emission is given by this. Alright, let's go to our next problem. Alright, okay, so our next problem is we have to estimate the lifetime of the upper state of a spectroscopic transition if the spectrum shows a peak with a full width at half maximum of this 0.01 centimeter inverse, 1.5 centimeter inverse, and 40 centimeter inverse. Now for this problem as well, for problem number 6, we will use the same lifetime broadening relation. So the lifetime broadening relation that is given by tau del E is equals to h plus, right? So this will now, okay. So let's denote full width half maximum by delta. Okay, so let's denote whatever our full width at half maximum. So we will have so what it's showing is that lifetime of the upper state of a spectroscopic transition when the sun shows a peak with a full width at half maxima, so which is given as a wave number. So we will denote this full width at half maxima by delta, which is a wave number. Now we will convert this delta from a wave number to an energy in joules multiplication by hc. Okay, so basically when we have this spectroscopic transition, okay, you have to find the transition. If the transition peak has a full width half maxima, so full width at half maxima, so that will be our basically the uncertainty. So what we are saying is that so this is the similar problem that we have solved earlier, and in that problem it was given that the uncertainty and that state is so if you remember the problem number what we did, problem number 3, yeah. So in problem number 4 we have a similar problem. We have to find the lifetime of a molecular state if the uncertainty in its energy. So uncertainty in the energy is what directly given. So we just applied the formula directly, like tau del E equals to h cross, and del E is already given. Now in this thing, in this problem, what is given to us is the full width at half maximum. Okay, so what is given to us is this thing, full width at half maximum. So that also, if you remember, so like if you have this broadening, so and if you have this full width, so that is also basically gives you your delta of E. Basically this thing will give you your uncertainty in your energy, alright, for your molecular state. So that is what we are doing. So this delta, and we will convert this into Joule energy. So our del of E, so if you do this, so this will, so what we will get is our del of E will be equals to Hc times delta. So our full width half maximum, in our spectral substitution, that will give us the delta of E. So basically if we have this kind of thing and we have full width at half maximum, this thing will be your delta of E. Delta of E, full width at half maximum. So if you have this energy versus width, and this is your maximum and this is your half. This is your maximum, let's say some so this width will be your delta E. Okay, so and the width is given as in this problem, like width is given in a form of wave number, Sankey inverse. So you just have to multiply by Hc, and that will be your delta E. So your tau lifetime from this lifetime broadening relation, we know we given by h cross by del E. So that will be equals to h cross divided by del E will be given by Hc delta. Alright, and this is h upon 2 pi. So that is equals to 2 pi c delta. H cross is h upon 2 pi. So basically you come to this formula, which is tau is equals to tau is equals to our lifetime is equals to 2 pi c delta. Alright, so this is the relation that we have to use in this problem. So let's say from part A, the delta is given 0.01. So tau will be equals to 2 pi times 3 into 10 to the power 10, which is the c speed of light, and per second. I'm just writing approximate times 0.010 centimeter inverse, pole inverse, and this if you calculate will be equals to 5.3 into 10 to the power minus 10 seconds, which will be equals to, which value is 530 picosecond. For B part, it is given that we have, it is 1.5 centimeter inverse, delta is 1.5. So here we will have our 2 pi times c is 3 into the power 10 centimeter second inverse, times our delta, and our delta is 1.5 centimeter inverse. So 1.5 centimeter inverse, whole inverse. That will be equals to 3.5 into 10 to the power minus 12 second, which is 3.5 picoseconds. Right, and then we have c tau delta is 40 centimeter inverse, and that is equals to 30 into the power minus 14 second, which will be 130 seconds. Alright, so here also one thing that you can see is that now the uncertainty del E will be in del E will be is given by hc time delta. So del E depends on your wave number. Alright. So as your delta E is increasing, so we are increasing the delta E, our lifetime is decreasing. Okay, so and that is the uncertainty duration as well. You can see, or you can see that basically if our you can see from different angle as well, as our lifetime is decreasing, as we are decreasing the lifetime, our uncertainty value, del of E value, that is increasing. So our uncertainty is increasing. So that you can see that we are getting the broadening. We will see broadening in our spectroscopic data. For the spectroscopic peak, there will be a higher broadening. This full width at the half maximum, this broadening, this delta E will be larger as our lifetime of our state is decreasing. So this delta, that's why the broadening will increase, or that uncertainty in the energy of that state will increase. So that we can see from our this relation as well, from this problem as well. Alright, now let's go to our next problem. So okay, so now in this problem, what is given to us that in an ensemble, okay, so we are given that, okay, in an ensemble of systems, let ni at t equals to 0 be the initial number of states in state I, in state get I. Now due to the perturbation Vt, okay, which is a time, okay, let's say gap of t or something, this ni of t will decrease with time with a constant rate given by the Fermi-Gordon rule. So we know that so basically this is the same thing. From the Fermi-Gordon we know that we go from initial state, and because of the perturbation it is going to some continuum of state, we can say, and that rate, so that will be the decay rate of our initial state I. So this initial number of states, initial number of systems, you can say, it is said initial number of systems. So this NIT initial number of system, so they will decrease as we apply the perturbation, and they will go to this continuum of some continuum of states, final states, which we know is given by our Fermi-Gordon rule. Now what we have to do is we have to find an expression NIT in terms of this Ni at t equals to 0 before the perturbation is applied, and W, the transition rate obtained from Fermi-Gordon. So in terms of the transition rate that is obtained from the Fermi-Gordon rule, W, that we are denoting as W, and the initial number of systems in the state, we need to find an expression for the number of systems in state I at any time t. Alright, so that is our problem. Now from Fermi-Gordon rule, we know that this W, coming from initial to final state, that will give me 2 pi h cross V of Fi square times rho of energy of T5, and that we are calling as W. Okay. Now in this question, we need to find answer in terms of this W only, so we don't need to calculate it. Okay, so we don't need to calculate, but we just need to remember that this is given by the Fermi-Gordon rule. So there is no even requirement, like we don't even actually need this. We will not need this formula. Alright. So this is our W transition rate, but we will not actually need this formula. Now, what I can write is that if the initial I know, so now this will be this W is the decay rate for state I. Alright, so this is the decay rate for state I. So our Ni times t plus delta t, I can write as Ni at time t minus Ni at time t times whatever our decay rate is times delta t. Alright, so this is how we will write Ni. This is how our number of systems for that initial state I will change at any time t plus delta t, because we know what is at t, and then what will be the change in delta t will be the whatever state Ni is times the decay rate or the change rate of change, which is minus W we are writing, because it is a decay rate. Alright, so we have this. Now from here I can write that Ni of t plus delta t minus Ni of t, that will equals to minus Ni of t W del t. Next I can write Ni of t plus delta t minus Ni of t divided by delta t equals to minus Ni of t times this W rate. Now for limit delta t tends to 0, or you can say dt finite decimal time. What we can write this as d Ni of t by dt is equal to minus Ni of t times W. Right? So we are getting a very simple relation. I can write it as d by Ni of t equals to minus W times dt. Now we just have to integrate it. So integrate it from 0 at what time we have applied the perturbation times at any time t. Let's say I say it is d of Ni t prime by d of Ni t prime, that is equals to minus W dt prime from 0 to t. That is this, that gives us ln of Ni of t prime from 0 to t equals to minus W t prime from 0 to t. So what we get is ln Ni of t minus ln Ni at t equals to 0, that will be equals to minus W times t. This we can write as Ni of t divided by Ni at t equals to 0 equals to minus capital W times t. Alright, so what we get is Ni of t will be equals to Ni of t equals to 0, it is equals to minus e to the power minus Wt exponential to the power Wt. Alright, so we have obtained the relation. Ni of t will be equals to Ni at t equals to 0 e to the power minus Wt. That is our answer. Alright, so So that is what here we just have to find an expression of NIT in terms of NIT equals 0 and the transition rate. So that is the answer. NIT equals 0 to minus WT, and this W we can find from if the details are given, which is we need to find as we have find in the previous question. We have find this V, and we have find the rho as well, rho radiation as well. So if there is transition matrix and we have to find transition matrix element and the density of states. So this information here, then we can find our W value. But in this question, we just have to find this one only. Alright. Okay. Let's check if recordings are. Right. Okay. Go back. Okay. So these are the problems for this session. Okay, so let's just let us go and alright, so we still have some time. We still have some time today, right? We have some time. So for next 20 minutes, okay, so let's just discuss the assignment 8 solutions as well. Discussion. Okay, sorry about that. Just recording properly. Alright, okay. So we have okay. So those are the sample problems for this session, and let us discuss the assignment 8 solution as well quickly. The first question was which of the following does do or does not change with time for a stationary state? The position of a particle, the probability density, the energy of the state, all of this. So we know that the position of the particle. So for the stationary state, we know that the basically the mod of psi square basically. Okay. So. Yeah. Basically the mod of psi square that is fixed, right? So we know that the mod of psi square will remain fixed, and also we know that the composition of the system, not the composition, basically the wave function will not change. So the energy of the state will also not change. So there will be no lifetime of our system. So the probability density and this psi h cap psi, that is also basically fixed with time, and this is also fixed with time. So basically that's why we have we can't say the position of the particle, that is not a stationary part. The probability density and which is this psi square, and the energy of state, which is given by this psi h cap psi, that are fixed with time. So the answer will be B and C, and that is in the detailed solution also given. The stationary state does not mean that the particle is at rest. It means that the probability density and other expectation values such as energy, they do not change. Alright, so that was problem number 1. Then in problem number 2, which of the following is or are examples of non-stationary state? Psi and Lm are the hydrogen atom eigenfunctions. So we need to find the non-stationary state. So going with the similar idea, now we have psi 10, psi 210. We have 1 by root 2 times psi 100 plus psi 20, or 1 by root 2 psi 20 plus psi 210. So if we write now is an example of non-stationary states. Now we have to find, we know that psi x comma t is given by summation n c n psi n x. So the time dependent wave function is given by this linear combinations of psi n x to the power minus i omega n t. This we can write, and then the mod square will be given by this, so there will be some time dependence. The function in A and B have definite energy and hence are now as we have said, for the stationary state we will have the definite energy because there is no time component to decomposition. But as given in the solution, the function in A and B have definite energy and hence are stationary states. The function in C is a linear combination of two functions with different energies, hence it is non-stationary. So here you can see that since these are just one state only, so their energy is fixed, and that we talk about in stationary states. Okay, so the stationary state will have two things: they have the fixed probability, and they will have probability density, and they will have the fixed energy of the state as well. So for A and B, the energy of the state is fixed. For state D, the psi20 since n value is same, so for this also the energy of state is fixed. So these are not the non-stationary state; these are the stationary state. While for the C, we have psi10 and psi20, so they have the different energy. So the energy of the state is actually will be a combination of, it's not fixed, and that's why they will give the non-stationary state, and that is given in the detailed solution. The function in A and B have definite energy and hence are stationary states. The function C in C is a linear combination of two functions with different energy, hence it is non-stationary. It is a linear combination of two functions with different energy, so its energy is not fixed. And the first stationary state, probability density and the energy of the system state, that will be fixed. Example in D shows a linear combination of two eigenfunctions with the same eigenvalue, hence the time factors will cancel out and the probability density. Okay, the time factor, as you can see, the time factor is given by omega n minus omega m. So this time factor will be cancelled out in case of D, and thus there will be no time component. But in case of C, since these are different energies, this will not cancel out, and we will get a non-stationary state. And the time factor will cancel out, and the probability density will be time independent, hence stationary. Alright. So moving on to so that's why the answer is C. Okay. Next question is, okay, a particle of mass m moves freely inside an infinite potential well of length a has the following wave function at time t equals 0. So at time t equals 0, it is given that particle mass m has f phi nx, which is the nth particle in a box eigenfunction with eigenvalues en. Alright. Now we are given a psi x comma 0, which is given by a linear combination of similar phi 1x, phi 3x, and phi 5x. What is the probability of finding a system at time t in the state phi x comma t, which is equals to so a particle of mass m moves freely, and okay, at t equals to 0 we have psi at x comma 0 is provided. And what is the probability of finding a system at time t in the state? So that is given by their coefficients at any time t, and since it is given that no perturbation is being applied, so these coefficients will not change with time. So the probability will be as same at t equals to 0, and it is for phi 5x phi 5 it is asking. So that is a, that is our coefficient a. So that is given by a square, coefficient e square. Now a is not given, so that will be just 1 minus the coefficient of phi 1 and phi 3. So 1 minus 3 by 10 minus 3 by 5 equals to 1 by 10, because probability of 5 will be just equals to mod of e square, which is equals to 1 minus probability of, you can write as 1, and probability of 3, and that is what you done. 1 minus 3 by 10 minus mod square 3 minus 3 by 10 minus 3 by 5 giving 1 by 10. So probability finding a system is 1 by 10, and that is answer E. Alright. Okay, and next is problem number 4. At time t equals to 0, the time dependent state of an electron in a 2 angstrom box is given by, okay, so time dependent wave function is given, where psi 1 and psi 2 are the ground and the first excited stationary states of particle in a box problem. What is the period of oscillation of this electron? Alright, so we need to find the period of oscillation. So psi x comma t, so if we are given psi, then we can write the psi x comma t as 1 by root psi 1x this, and mod of psi square will be given by this, and you can write it in this cos form. I guess that will be equals to here we know this just 1 cos omega 2 1 t. Now the period of oscillation of the electron is from cos omega 2 1 t oscillation. So okay, so what is the period of oscillation? So basically period of oscillation will be just we know the psi x comma t psi as a function of t, we know, and you just have to find the probability density. You have provided probability density, and this frequency and this oscillation is given by omega 2 1. So we just need to find omega 2 1, and En we know n square by 8 ml square is given by this. So you can just put those values, and you can find the omega 2 1 comes as this. So and that period of oscillation will just be 2 pi divided by omega 2 1, because this is in seconds, and that you can calculate to be 1.5 to 10 power minus 16 seconds. Alright, so that's my answer will be A. Okay, then question number 5. When a weak and a constant perturbation is applied to a two-state system, what happens to the population of the initially empty state? So it can become 1. Okay, so a weak and a constant perturbation, it can become 1 if the two states are degenerate. So this we have seen if the two states are degenerate, and we have seen that from the in our problems, also the sample problems that we solved from the Rabi's formula. We find that when it is degenerate, we get this P2T is equals, if you remember, P2T comes as sine square mod of Vt, and so it is given that it is a weak and a constant perturbation. So even if it is weak, but for the degenerate state, P2T comes as this, and it can become 1. What happens to the population of the initially empty state? It will become 1, because we will get a sine function, and even if this mod of V is small, at some time it will become 1. So okay, so that's why the answer will be A. Alright, so that is just a simple question from the formula, and let us see the detailed solution. So that is the complete Rabi's formula. There will be a sign here, sine square. Alright, so when two states are degenerate, we know that P2T will be given by sine square mod of Vt, and even when there will be again a sign. So the formula is just written from here, but you know, okay, basically for degenerate state this will be the formula. So hence even weak perturbation can lead to complete transfer of population. If the two states are well separated, the strength of the perturbation and the separation of states would determine the extent of population transfer. So what is extra is given that if the two states are well separated, the strength of the perturbation and separation of states would determine the extent of population transfer. Very strong perturbation can lead to complete transfer of population. So the strength of the perturbation and the separation of the states, that they might affect the extent of population, but the probability can become the population this probability can become 1, we know from this formula, even if the potential is weak. Okay, next question. This is problem 5 or number 6. Which of the following is true for an Einstein coefficient? We know that BFI is equals to BIF. We just saw it in the sample problem, right? And they don't have the same units. If you remember, when we solved the problem, we find that A will have the second inverse unit, while B doesn't have. It will not have this unit. Okay, problem number 7. Now, how does the population of an initially empty state vary with time in case of a slowly switched constant perturbation for a given coupling strength between the two states? So we know that population, what we have slowly switched the constant perturbation, and you have seen you have seen in the lecture that the population increases with time, and it eventually attains equilibrium. So the population of the empty state increases with time and gets steady after a long time. So you can go to the lectures and you can see that you have seen this curve, and if you apply very high frequency, then there is fluctuation is more, but afterwards it will attain the equilibrium. Okay, so the answer is B. Now, which of the following is true for the transition rate from one energy state to a group of energy state in a continuum as a result of weak perturbation? Now, this is given by the Fermi's Gordon rule, which is given here by h square vfi square rho. So, what are things which are true? The transition rate increase. Now, the transition rate will be given dp by dt, and the dp by dt, you know, okay, this is not a Fermi's Gordon rule. This is basically the transition variability, and the Fermi's Gordon rule is this, which is dp by dt is given by 2 pi h cross this, and we know that there is no time dependence, so there is no time dependence. Transition rate is independent of time, and the answer is C. This is the Fermi Gordon rule. Let me just see today's session. Now, okay. Now, question number 9. In which of the following emissions the rate of stimulated emission will be the highest as compared to the rate of spontaneous emission? So we know this relation is given. This is the relation between spontaneous emission, which is A, and the stimulated emission, which is B. Now, what is that? You can see that in this, basically, if the frequency is greater the frequency, higher is the rate of spontaneous emission. Okay, so if the frequency is higher, then the spontaneous emission will also be higher. So you just have to convert this thing, this into same units of frequency, and then you can find. Now here also this is nanometer. I guess the C will cannot be answered because it is I guess this is in wavelength, so you have to check, I guess, convert all the values into the energy units, and maybe compare from there. And whichever, and what we have to find here, the rate of stimulated emission will be the highest, so you have to find the stimulated emission. You need stimulated emission to be highest, so the lowest frequency, you need to find the lowest frequency. Spontaneous emission, but we need the stimulated emission to be highest, so we need the lowest frequency. Alright, so the answer will be D. We just have to convert the units. Okay, in next question, what is the lifetime tau of the upper state of a spectroscopic transition if the emission spectrum shows a peak with a full width half maximum, that delta equals to 1 centimeter inverse? So we have just solved the similar problem. So our tau will be equals to, now here energy time uncertainty relation, that is taken as h cross by 2 del of E. So here the constant has been taken as h cross by 2. We have taken in our sample problem, we took it as h cross. So that could be taken, that is just a constant thing. So basically it is del E, and this del E is basically given by, we have given 1 centimeter inverse, and as we solved in our sample problem, you just have to multiply this delta with hc. You have to multiply it by h and c, and so your tau, you can find that it will be h cross by 2. You will multiply by hc by your delta. Your delta is given by this 1 centimeter inverse here. So that will be equals to, we will have 4 pi c delta. Alright, and let's just find this. So you can find that equals to 4 pi times 3 into 10 to the power 10 centimeter second inverse times delta is given as 1 centimeter inverse. Alright, 4 inverse. So this let me just calculate 3 so we will get something 2.65. So if you calculate this, I just calculated. So you will get 2.65 times 10 to the power minus 12, which is pico 2.65 picosecond. 10 to the power minus 12 is picosecond, and that is our answer, 2.65 picoseconds. Alright, so we solved a similar problem in our sample problems as well. So you can solve this, and those are all the problems in from assignment number 8. Alright, just go back to our problems. Alright, so I guess our session is also over. Okay, yeah. So so those were all the problems. So we basically discussed quite some problems regarding the weak content, which was like time dependent perturbation theory. So mostly we actually use the formulas that were derived in the lectures and how to use them, and we also see their basically we saw their applications in the problems. Alright, so that's all the time we had. Okay. Thank you for your time and attention.